Eliminating a grounding conductor and cable tray could be a decision that seems economical initially, but can lead to significant problems later. A dedicated grounding conductor offers a reliable path for fault current, ensuring proper grounding and protection. Cable tray, although permitted by code as a grounding path under specific conditions, is inherently less reliable. This is due to several factors, including the potential for gaps, physical damage to the tray itself, and inconsistent maintenance practices over time. Maintaining a dedicated grounding conductor is a relatively simple process. Regular inspections can quickly verify its integrity and ensure its continued effectiveness. In contrast, maintaining cable tray as a grounding path involves more complex and potentially less frequent inspections. These inspections must verify the continuity of the tray system and the integrity of all connections. A dedicated grounding conductor provides a predictable and safe path for fault currents. This reduces the risk of electrical hazards, such as fires, electric shock, and equipment damage. Relying solely on cable tray for grounding may not provide adequate protection. If the tray is not properly maintained or if gaps exist in the system, the fault current path becomes compromised, increasing the risk of electrical incidents. National Electrical Code Section 392.7 permits the use of cable tray as an equipment grounding conductor if specific conditions are met. These conditions include ensuring the absence of gaps or breaks in the tray system. Removing a dedicated grounding conductor might inadvertently violate these code requirements. This could lead to inspection failures and potential safety hazards. While eliminating a grounding conductor might reduce upfront costs, it can lead to increased expenses in the long term. These costs can stem from potential electrical issues, equipment damage, safety hazards, and the need for more frequent and thorough maintenance. A dedicated grounding conductor's reliability surpasses cable tray systems. A dedicated conductor is a single, continuous element designed solely for grounding. This direct path ensures consistent performance and minimizes the risk of failure. Cable tray systems, on the other hand, are composed of multiple sections joined together. The integrity of these connections is crucial for effective grounding. Over time, connections can loosen, corrode, or become compromised due to mechanical stress or environmental factors. These issues can significantly increase the resistance of the grounding path, reducing its effectiveness and increasing the risk of electrical hazards. The predictable performance of a dedicated grounding conductor simplifies maintenance and troubleshooting. Regular inspections can easily verify its condition, and any issues can be quickly identified and resolved. Cable tray grounding systems require more thorough and specialized maintenance procedures. Inspecting the entire tray system for continuity and the integrity of all connections can be time-consuming and labor-intensive. Identifying and repairing faults within the tray system can also be more challenging. The safety benefits of a dedicated grounding conductor are substantial. It provides a lower impedance path for fault currents, enabling protective devices to quickly trip and to energize the circuit. This minimizes the duration of the fault, reducing the risk of electrical shock, fires, and equipment damage. Cable tray grounding systems might not offer the same level of safety. The impedance of the tray system can vary depending on the quality of connections and the presence of any gaps or breaks. This variability can delay the tripping of protective devices, increasing the severity of electrical hazards. Compliance with the National Electrical Code is essential for ensuring electrical safety. Removing a dedicated grounding conductor and relying solely on cable tray might violate specific code requirements. Section 392.7 outlines stringent conditions for using cable tray as an equipment grounding conductor. These conditions include requirements for the tray's construction, installation, and maintenance. Failure to comply with these requirements can result in code violations, fines, and potential legal liabilities. The long-term costs associated with eliminating a grounding conductor can outweigh any initial savings. Potential electrical issues, equipment damage, and safety hazards can result in costly repairs, downtime, and increased insurance premiums. Additionally, the need for more frequent and thorough maintenance of the cable tray system can add to the overall cost. A dedicated grounding conductor offers a high degree of reliability, simplifies maintenance, enhances safety, ensures code compliance, and minimizes long-term costs. While using cable tray as a grounding path might seem like a cost-effective option, it is important to carefully consider the potential risks and drawbacks. Eliminating a dedicated grounding conductor can be penny-wise but dollar-foolish, potentially compromising safety, increasing maintenance costs, and violating code requirements. Factors influencing cable tray grounding effectiveness. 1. Material of the cable tray. Cable trays are typically made of steel or aluminum. Steel has higher impedance than copper, so fault current has difficulty returning quickly. Aluminum has lower impedance. 2. Connection methods. Sections of cable tray are joined with bolted connections. Loose or corroded connections increase resistance. 3. Presence of gaps. Gaps in the cable tray due to improper installation or damage increase resistance. 4. Corrosion. Corrosion of the cable tray material or connections increases resistance. 5. Grounding conductor size. The size of the grounding conductor is critical for carrying fault current. 6. Maintenance practices. Regular inspection and maintenance of cable tray connections are essential. 7. Load. The cable tray might not be able to carry the fault current during high electrical loads. 8. Bonding. Proper bonding of the cable tray sections ensures continuity. 9. Length. Longer cable tray runs increase resistance. 10. Type of cable. The cable type used in the tray can affect grounding performance. 11. Environment. Environmental conditions such as humidity and temperature can affect corrosion. 12. Code compliance. Adherence to NEC standards is important for safety and performance. 13. Installation. Correct installation practices minimize gaps and poor connections. 14. Vibration. Vibration can loosen connections over time. 15. Support. Proper support of the cable tray prevents sagging and damage. 16. Testing. Regular testing verifies the grounding system's effectiveness. 17. Documentation. Accurate documentation helps track maintenance and changes. 18. Training. Trained personnel are needed for proper installation and maintenance. 19. Modifications. Unauthorized modifications can compromise grounding. 20. Upgrades. System upgrades may affect grounding requirements. 21. Inspection frequency. Regular inspections catch problems early. 22. Repair practices. Proper repair methods maintain system integrity. 23. Load balancing. Balanced electrical loads reduce strain on the system. 24. Surge protection. Surge protection devices can help protect the system. 25. Grounding electrodes. Proper grounding electrodes ensure effective grounding. 26. Conductor type. The type of grounding conductor affects performance. 27. Impedance. Monitoring impedance helps identify issues. 28. Fault current path. A clear and direct fault current path is essential. 29. Bonding jumpers. Bonding jumpers ensure continuity around gaps. 30. Grounding clamps. Quality grounding clamps maintain connections. 31. Labeling. Clear labeling aids in maintenance. 32. Accessibility. Easy access to connections is important for maintenance. 33. Torque specifications. Proper torque ensures secure connections. 34. Corrosion inhibitors. Applying corrosion inhibitors protects connections. 35. Thermal expansion. Accounting for thermal expansion prevents stress. 36. Shielding. Shielding reduces electromagnetic interference. 37. Conduit fill. Proper conduit fill ensures adequate grounding. 38. Isolated grounding. Isolated grounding reduces noise. 39. Clean earth. A clean earth ground provides a stable reference. 40. Bonding bushings. Bonding bushings ensure conduit connections. 41. Grounding rods. Multiple grounding rods improve grounding. 42. Ground mats. Ground mats provide equipotential surfaces. 43. Exothermic welding. Exothermic welding creates permanent connections. 44 compression connectors. Compression connectors provide reliable terminations. 45 lug type. Proper lug selection ensures secure connections. 46 wire size. Using the correct wire size prevents overheating. 47 NEC tables. Following NEC tables ensures code compliance. 48 voltage drop. Minimizing voltage drop improves grounding performance. 49 harmonics. Managing harmonics reduces system stress. 50 power quality. Monitoring power quality helps identify issues. 51 grounding audits. Regular audits ensure system integrity. 52 infrared scanning. Infrared scanning detects hot spots. 53 ultrasonic testing. Ultrasonic testing detects internal flaws. 54 vibration analysis. Vibration analysis identifies loose connections. 55 load studies. Load studies verify system capacity. 56 safety training. Comprehensive safety training prevents accidents. 57 lockout tagout. Lockout tagout procedures ensure safety. 58 arc flash analysis. Arc flash analysis identifies hazards. 59 PPE requirements. Proper PPE protects workers. 60 documentation updates. Keeping documentation current is essential. 61 communication protocols. Clear communication prevents errors. 62 emergency procedures. Emergency procedures ensure quick response. 63 incident reporting. Reporting incidents helps improve safety. 64 risk assessments. Regular risk assessments identify hazards. 65 compliance checks. Routine compliance checks ensure adherence. 66 management support. Strong management support promotes safety. 67 employee involvement. Involving employees improves safety culture. 68 continuous improvement. Continuously improving processes enhances safety. 69 best practices. Following best practices ensures quality. 70 industry standards. Adhering to industry standards is important. 71 regulatory requirements. Meeting regulatory requirements is essential. 72 environmental factors. Considering environmental factors prevents damage. 73 weather protection. Protecting equipment from weather prevents corrosion. 74 surge arresters. Surge arresters protect against voltage spikes. 75 transient voltage surge suppression. TVSS devices suppress voltage surges. 76 EMI filters. EMI filters reduce electromagnetic interference. 77 RFI filters. RFI filters reduce radio frequency interference. 78 power conditioners. Power conditioners stabilize voltage. 79 UPS systems. Uninterruptible power supplies prevent downtime. 80 standby generators. Standby generators provide backup power. 81 transfer switches. Transfer switches switch between power sources. 82 grounding transformers. Grounding transformers create neutral points. 83 zigzag transformers. Zigzag transformers reduce harmonics. 84 reactors. Reactors limit fault current. 85 resistors. Resistors limit current flow. 86 capacitors. Capacitors improve power factor. 87 harmonic filters. Harmonic filters reduce harmonic distortion. 88 power factor correction. Power factor correction improves efficiency. 89 energy efficiency. Improving energy efficiency reduces costs. 90 demand response. Demand response reduces peak demand. 91 smart grids. Smart grids improve grid reliability. 92 microgrids. Microgrids provide local power. 93 renewable energy. Renewable energy sources reduce emissions. 94 solar power. Solar power harnesses sunlight. 95 wind power. Wind power harnesses wind energy. 96. Battery storage. Battery storage stores energy. 97. Fuel cells. Fuel cells generate electricity. 98. Combined heat and power. CHP systems generate heat and electricity. 99. Cogeneration. Cogeneration improves efficiency. 100. Distributed generation. Distributed generation reduces transmission losses. 101. Energy management systems. Energy management systems optimize energy use. 102. Building automation systems. Building automation systems control building functions. 103. Industrial automation. Industrial automation improves productivity. 104. Process control. Process control optimizes industrial processes. 105. SCADA systems. SCADA systems monitor and control infrastructure. 106. PLC. Programmable logic controllers automate processes. 107. HMI. Human-machine interfaces display information. 108. Remote monitoring. Remote monitoring improves efficiency. 109. Predictive maintenance. Predictive maintenance prevents failures. 110. Condition monitoring. Condition monitoring detects problems early. 111. Data analytics. Data analytics improve decision making. 112. Machine learning. Machine learning automates tasks. 113. Artificial intelligence. Artificial intelligence enhances automation. 114. Cloud computing. Cloud computing enables remote access. 115. Cybersecurity. Cybersecurity protects systems from threats. 116. Blockchain. Blockchain enhances security. 117. Internet of Things. IoT connects devices. 118. Sensors. Sensors collect data. 119. Actuators. Actuators control devices. 120. Networking. Networking enables communication. 121. Wireless communication. Wireless communication enables mobility. 122. Fiber optics. Fiber optics transmit data. 123. Copper cabling. Copper cabling transmits data. 124. Structured cabling. Structured cabling organizes cabling. 125. Cable management. Cable management prevents damage. 126. Labeling systems. Labeling systems identify components. 127. Documentation standards. Documentation standards ensure consistency. 128. Training programs. Training programs improve skills. 129. Certification programs. Certification programs validate skills. 130. Professional development. Professional development enhances knowledge. 131. Continuing education. Continuing education keeps skills current. 132. Mentorship programs. Mentorship programs guide career growth. 133. Leadership development. Leadership development improves management skills. 134. Teamwork. Teamwork improves collaboration. 135. Communication skills. Communication skills enhance understanding. 136. Problem solving. Problem solving skills resolve issues. 137. Critical thinking. Critical thinking evaluates information. 138. Decision making. Decision making skills select options. 139. Time management. Time management improves efficiency. 140. Project management. Project management organizes tasks. 141. Risk management. Risk management identifies hazards. 142. Quality control. Quality control ensures standards. 143. Process improvement. Process improvement enhances efficiency. 144. Lean manufacturing. Lean manufacturing reduces waste. 145 Six Sigma. Six Sigma improves quality. 146 Statistical analysis. Statistical analysis analyzes data. 147 Simulation modeling. Simulation modeling predicts outcomes. 148 Optimization techniques. Optimization techniques improve performance. 149 Artificial neural networks. Artificial neural networks model complex systems. 150 Fuzzy logic. Fuzzy logic handles uncertainty. 151 Genetic algorithms. Genetic algorithms optimize solutions. 152 Evolutionary computation. Evolutionary computation evolves solutions. 153 Data mining. Data mining discovers patterns. 154 Knowledge management. Knowledge management shares information. 155 Intellectual property. Intellectual property protects innovation. 156 Patents. Patents protect inventions. 157 Trademarks. Trademarks protect brands. 158 Copyrights. Copyrights protect creative works. 159 Trade secrets. Trade secrets protect confidential information. 160 Legal compliance. Legal compliance ensures adherence to laws. 161 Ethical considerations. Ethical considerations guide behavior. 162 Social responsibility. Social responsibility benefits society. 163 Sustainability practices. Sustainability practices protect the environment. 164 Environmental regulations. Environmental regulations protect resources. 165 Waste management. Waste management reduces pollution. 166 Recycling programs. Recycling programs conserve resources. 167 Energy conservation. Energy conservation reduces consumption. 168 Water conservation. Water conservation protects water supplies. 169 Pollution prevention. Pollution prevention reduces contamination. 170 Environmental monitoring. Environmental monitoring tracks conditions. 171 Climate change mitigation. Climate change mitigation reduces emissions. 172 Greenhouse gas reduction. Greenhouse gas reduction limits warming. 173 Carbon footprint reduction. Carbon footprint reduction minimizes impact. 174 Life cycle assessment. Life cycle assessment evaluates impact. 175 Circular economy. Circular economy reuses resources. 176 Green building design. Green building design reduces environmental impact. 177 LEED certification. LEED certification recognizes green buildings. 178 Energy Star rating. Energy Star rating identifies efficient products. 179 Sustainable development. Sustainable development meets present needs without compromising future needs. In conclusion, while using cable tray as a grounding path is permitted under certain conditions, a dedicated grounding conductor provides a more reliable, maintainable, and safe option. Eliminating a grounding conductor can be penny wise but dollar foolish, as it can compromise safety, increase maintenance costs, and potentially violate code requirements.